Okay, so we're going to have a quick look at the starter solenoid here. I've just done a drawing out here just to give us an insight into what's inside it here. So here's our starter solenoid here and our starter motor down below it here. I'm not showing the pinion as of yet, but just a basic, just because it's up here really we're looking at. So the starter solenoid itself has these two big terminals on it here, right? The top one being the B plus here, which takes a wire directly back to the battery positive. The smaller one in the centre here being the S terminal, which goes to the starter relay, and that's controlled then by the starter switch. And then our link one here, which links our solenoid to our motor, the M terminal on it here, right? So at rest, what we have is this going on here. We have our plunger here, which we want to create an electromagnet inside our solenoid here and draw that plunger in here. In so doing, this bridging plate that's here is going to push forward and bridge out between this terminal and this terminal. Now our battery voltage has a pathway to come in, cross the bridging plate, out, down into the motor, and then down through the motor where it's earthed from the engine and back to the battery through the straps that are there. So inside our solenoid itself we have two windings. One is a pull-in winding here and one is a hold-in winding here. So the pull-in is in green and the hold-in is in red. Both of those windings, their start point is here on the S terminal, right, for the starter signal here, right? And it's a parallel circuit here. You can see the green parallels out this way, comes around, goes through its windings and comes back to the M terminal here and finds its earth then through this into the motor part, because inside here this will go in onto the positive brush. We have our armature inside there then, and out the other side of it we will have our negative brush going out to earth on the through the starter motor itself here now. So that's the pull-in's route to earth. When we power this up and give it a turn from the 50 on the key, current will come in, power through that green winding, come all the way around the coils in it, back out through the M here, link down through the positive brush, across the commutator and motor, and out to earth through the casing itself here. On the other hand, the hold-in winding comes in parallel out here, comes down through the hold-in winding and goes straight to earth through the casing here and out to the casing. So it doesn't have to go through the armature and brushes there. And remember, current will always take the path of least resistance, so if it doesn't have to go through this brush, it will take out here. But there are two separate windings in here, the hold-in and the pull-in. Now, let's talk about what happens when we send the starter signal. We're going to push a current down through here. An electromagnetic field is going to be created inside the pull-in and the hold-in windings, so we're going to get a strong electromagnetic field. At that stage, that plunger is going to get pulled in inside the solenoid here, because it's attracted in by the magnetic field here we've just created. Once that bridging plate comes across and hits that point and that point, look what's just happened. We have a 12 volt then coming in on this pull-in winding, going all the way around the end here, and it's a 0 volt here initially because it's out to earth. But once that bridging plate hits that pin, I no longer have a 12 volt there, or a 0 volt, I have a 12 volt coming from here across the bridging plate. So if 12 volts pushing in on the pull-in winding and 12 volts at the other end of it, which means I've two 12 volts trying to push, which means I get zero current flow. So I've effectively bridged out that pull-in winding. So the only thing that's holding the plunger in then is the magnetic field from the hold-in winding. So what we want to do is take a look at testing this as a unit by itself here, right? But we can see everything we need is here on it. It's telling us how it works. Now, obviously, that plate stays up against these pins here as it's bridged, so it comes across like this, bridges out those two plates, now heavy current from the battery can come in across the plate and out into the motor and out through the negative brush, goes through the motor armature here and out to the negative brush out to air through there, and our motor starts to turn. But our pull in first happens here for our plunger. It has to get pulled inside here. There's also a fork linking from this end, pulling a plunger or pushing the pinion into engagement with the ring gear, and then the motor starts to rotate. So it's like a two-stage. We must engage the pinion first with the ring gear and flywheel, and then rotate the motor, right? So what we're going to have a quick look at here is how to test this armature here in reality, right? So what really I'm looking at is, are my two windings in here in good condition, right? Are they closed circuit? Are they all right? Because if one of them goes open circuit, I've lost my pull in. I won't have generate enough of a magnetic field to pull that plunger inside, engage the pinion with the ring gear. So both of them have to be working well. So all we're doing is a little test on them here, right? Now, if we look here and said, right, if I wanted to test this pull-in winding here, if I put 1 point of my meter on a resistance test on the S terminal, and then where does the other end of that winding go? It goes to the M terminal. So just go across the two of them with my ohm meter and get a reading for my pull-in winding. Write down whatever the resistance is on it, and then leave one pin there on the S and go to the body of the actual solenoid. And that way we're checking the resistance down this red wire here out, and there's our whole end winding. So what we'll do is we're just going to have a quick look at how to do this here now. So here's our starter solenoid here, and we have our 3 terminals here, our B plus, our M, and our S here, right, on this small push on connector here, right. So again, all we're doing is a resistance test on these. We've set up our meter. So again, remember, when you're setting up your meter to measure resistance, pull the red wire out, look for your resistance pole here, and it's here, our connector here, our jack, push our wire in there, and then look for resistance here. Now this is an auto ranging meter, remember, so remember we have to zero out all the time when we're doing resistance, because we want to test the resistance of the component, not the resistance of the leads as well. So if I just connect them together, let them sit there, I'll get the internal resistance of the leads. So when I do this test, I know I have to take the internal resistance of the leads off it. So this one here, we'll have 0.4, 0.5 of an ohm to come off it. So again, simple test. Let's go for our S. Now remember, when we're connecting a meter to measure resistance, we connect in series with the component disconnected, right? So you don't need essentially to take it off the motor, but once the wires are disconnected off it, right? So we have our S wire disconnected and our B plus wire disconnected. So what we want to do then is connect in series to measure resistance. Sorry. Use this one here, it's a little bit easier to do it now. So again, onto our S terminal there, and this would be our B plus here, so we just go across it and let it settle down. Now remember, there'll be low enough resistance in these. So what have we got? We have about a 1 ohm resistor in our pull-in. So if we said up here, we'll put it down as 1 ohm resistor there for our pull-in. Now remember, we have to take our 0.5 off this, so about 0.5 of an ohm in total. Because if we say that's reading 0.91, so we settle down there 0.9, take 5 off it, or 0.5 off it, because that's inside our leads, which brings us down to 0.4 of an ohm in our pull-in. And if we want to check our hold-in, then again we leave one wire connected. And remember, there's no polarity really for resistance, it doesn't matter, and go to the casing. Anywhere on the casing there will do me. And again, we have a 0.5 of an ohm resistor to take off it, or resistance to take off it. So we're about, what are we? 1.4 of an ohm minus 0.5, so about 0.9 of an ohm on our hold-in winding. And that's normally the way it will be. Our pull-in winding will have less resistance. Therefore, if it has less resistance, it's going to have more current. And our hold-in winding, which is the only one that's left working while we hold the key on, will have a bigger resistance, which will be a smaller current. Therefore, ensuring we get the majority of current going directly into the motor so we can make it turn. So let's just do a little sum here on these and see where we're at. And remember, these are like parallel calculations again. So if we draw our tree, and we want to find out what the total resistance is. Resistance total, this is resistance 1, resistance 2, so resistance 1 is equal to our pull-in, and resistance 2 is equal to our hold-in. And our pull-in resistance was 0.4 of an ohm, and our hold-in resistance was 0.9 of an ohm. Now we can try and work out from that what our total current will be through the circuit. So remember, our formula for resistance total, R1 times R2 divided by R1 plus R2. So what we end up with is 0.4 multiplied by 0.9 divided by 0.4 plus 0.9. Our top line then works out at 0.4 multiplied by 0.9. So that leaves me with 0.36 on top here, and 0.9 plus 0.4 is 1.3, which gives me a total of 0.36 divided by 1.3, which equals 0.276 ohms resistance total. So 0.276. Now, if we look and see, right, what was going to happen here was we have that, so our total current when both those windings are briefly powered up together is going to be, from our Ohm's law, it's going to be 12 volts. We have 0.276 ohms. So 12 divided by 0.276 is going to be 43.47 amps, which is quite a large current, right? But very briefly, right? So let's see what each one is going to pull out of that. If we go back and do one for each, a current for each. So R1, our pull-in winding, we're saying had 12 volt feed and 0.4 of an ohm. So 12 divided by 0.4 equals 30 amps in our pull-in, and our hold-in then had 12 divided by 0.9, which left us with 13.33 amps in our hold-in. So there are two currents that are actually going down to it. Remember, our pull-in, this one here, which is the highest current, only works extremely briefly, just to create that initial magnetic field to pull that plunger inside, and then it's bridged out and that current is gone. So that it leaves us with a current flowing through the hold-in winding of 13.33 amps. Okay, now even at that, they're quite high, and you'll notice for a huge amount of this is off a really old car, for a huge amount of modern starter motors, we'll see on our starter relay circuit is probably fused for about 30 amps on it, so it wouldn't quite be that high in total. The 43 amps, normally it'll be up around the 30, maybe 40 amps for the starter circuit, depending on obviously the size of the starter motor and solenoid. So basically that's it for our solenoid test. A very easy test to remember to do again, right? So remember, everything stems from this start pin here, right? This one here, and it bridges out two ways. One winding goes to the M, which is going to give us our pull-in figure. Give us our pull-in figure, and we take off whatever our resistance is of our leads. So remember, every time you're doing this for resistance, bridge out them and find out what the resistance of those leads are before you go measuring resistance of the component, right? So we have about 0.4 there of an ohm on that. Again, from our S terminal to our M terminal for our pull-in, and whatever it shows us here now, we take 0.4 off it. So 0.9, yeah, minus 0.4, so about 0.5 on that 0.8, yeah, brings us back down. And again, leave it on here and go for our hold-in anywhere on the casing at all, and we should see our hold-in winding resistance on that. And don't forget then, again, we have to take our lead resistance, or internal resistance of our leads, and our meter off it, to make sure we're only recording the resistance of the component itself. Okay, all right, thank you.